Hi everybody, this is Guillaume and I'm going to give you a quick preview of what I'm going to present at my PhD defense on April 28th. And the title of my thesis is Full Waveform Inversion by Model Extension. In plain English, the goal of my work is to use seismic recordings measured at the surface of the Earth to estimate the speed at which seismic waves or sound waves travel through the ground. And as you will see, this can help us create accurate maps of the subsurface without having to dig or to drill. So seismic exploration begins by sending sound waves into the ground, thereby interrogating the Earth. And when a wave hits an interface between two rock layers, a fraction of the energy is reflected back up to the surface and then measured. And from these recordings, we're going to be able to infer the structure of the Earth by creating maps. In this thesis, I will discuss this method in the context of hydrocarbon exploration, but it can definitely be applied to many other fields, such as global seismology, geothermal energy, or even finding traps to store the CO2 from the atmosphere. Seismic imaging, or exploration, is composed of 3 steps. In the first step, we acquire seismic data. So we're going to deploy a seismic vessel at the surface, and the seismic vessel is going to tow a seismic source, which is going to be sending the wave. And an array of sensors are going to record the pressure changes caused by those seismic waves. Okay, so here we're going to look at a seismic wave propagating through the ground. So here we can see some reflected energy going back up to the surface. And the wave continues to propagate until the wave hits those sensors, and the recorded signal from those sensors is called the seismic dataset. And this panel is an example of such dataset. And in the next phase, we're going to conduct what we call velocity estimation, which is the focus of my PhD. Velocity estimation requires the seismic data as input, and the output is the velocity model. And here on the right panel, the colors correspond to the speed at which waves propagate into the ground. So once you've got a good velocity estimation, you move on to the third and last stage, which is migration. So migration requires as an input some seismic data and a velocity model, and the output is what we call the migrated image. And those migrated images or maps indicate the presence of interfaces between rock layers, and they're quite higher resolution than the velocity model, as you saw before. As you can see here, the velocity model is way smoother, so lower resolution. And migrated images are quite important because they're then interpreted and we can infer the structure of the Earth with more accuracy. So in short, seismic exploration or seismic imaging is extremely important and useful. And also, developing algorithms to improve our knowledge of the subsurface can have a huge business impact. And more specifically, you'll see that the second stage, namely velocity estimation, is extremely challenging but crucial to obtain accurate images of the subsurface. And this is exactly why I decided to tackle this problem for my PhD. So if you want to know how I solved the problem, come to my defense on April 28th in the Hartley Conference Center at 8:30 a.m. I really hope to see you there.